So that last problem was pretty intense. Let's keep moving along on our handout. We're getting there. We're almost through. But let's look at the next page where we talk about more on the graphs of inverse functions. So suppose that f is a one-to-one function with inverse f inverse. We have already observed that if AB is a point on the graph of f, then BA is a point on the graph of f inverse. If we graph both the original function f and its inverse in the same coordinate system, we can see that each graph is a reflection of the other through the line y equals x. The line y equals x just is a straight line of slope 1 and y-intercept 0. It's like 1x plus 0 is its mx plus b form. And so it just rises up like a diagonal like this in an xy plane. And so if you have a function and its inverse, they're going to be symmetric around that line, y equals x. Now, I always thought that was a difficult picture to look at. So I want to show you another way to think of the relationship between a graph of a function and its inverse. And I drew a picture here of the graph of y equals x squared. Let me back out a little bit because this is really large. And we're familiar with that y equals x squared. I'm sorry, y equals x cubed graph. And now when we want to get an inverse for a one-to-one function like this, we want to change the role of the inputs and outputs. We really want to interchange x and y. Outputs become inputs, inputs become outputs. So graphically, it's kind of like we just want to interchange the x and y axes. So now if you try to put x in the y-axis position, you're tempted to kind of do something like this. But this isn't okay because the y-axis can't point that way. When you interchange the axes, what I want to do is I want x pointing up and I want y pointing to the right, right? So if you try turning a piece of paper, there's no way to get that to happen. But there is a way to get that to happen if we turn our piece of paper over. And I think this, luckily I used a Sharpie that went right through the sheet of paper here. Notice that my old x-axis is pointing straight up. My y-axis is pointing to the right. And what I see here is a graph of the inverse of the cube function. This is the cube root function graph. And that's a nice little trick to know, that you can always take the graph of a function and see its inverse by interchanging the x and y axes. But to do that, you need to turn the sheet of paper over. That's the only way to make it work. And so you need, you need paper that's not too opaque. That's a good little way. To me, that's the way I think of the relation between the graph of a function and the graph of its inverse. So let's go ahead and do exercise 5. And this is another one of these, well, let's see, we got a square root involved here. There's not much to the statement. I recopied it right here, so we're just going to go ahead and do the work. This is go through the process of finding an inverse function, right? So I'm going to rewrite the function. Let me just recopy it here. As y equals the square root of x minus 2. And I want to solve for x. So here I'm going to square both sides. And this is none of that, no plus or minus. This is not square rooting. This is squaring both sides. I can do that. And y squared then is equal to just x minus 2 because the square root cancel out. And now to solve for x, I just have to add 2. And I have x solved for. So I can switch the variables, right? And let's see here, I can write that as y equals x squared plus 2. And now I can write inverse. Okay, now I got a quadratic function here. There's something a little bit off, because how do I get a quadratic function that's not one-to-one out of all of this? So let's think about this a little bit. Let's go back to our original function and let's draw a graph. It's easy for us to draw a graph now because we know our transformations. We know this is the square root graph shifted 2 units to the right horizontally. So it's going to kind of be in that position. Okay. And here it is. I just happen to have one of these Sharpie copies of that function. Now, if I want to imagine the graph of the inverse, so F inverse, I'm going to write that alongside. Now, it's not hard for us to sketch a graph of that, I hope, when you see x squared plus 2. But I'm going to work from this picture right here and interchange the x and y axes like I was just talking about a moment ago. And notice that what we get here is this, again, curve with this point now on the y-axis, right, when we turn interchange, curving off to the right. That's just half a parabola. So we didn't realize it, but the F inverse really needs to have a restricted domain. With restricted domain, let's see, the domain for this picture, this would be from 0 to infinity. So that's kind of the fine print in this problem number 5. I would say the answer is yes, x squared plus 2. But that's an entire U-shaped parabola. And we don't want the entire U-shaped parabola. Here we should only get half of it, because the graph has to come from this square root graph, which is only half a parabola to begin with. Notice that the domain of f, we can see from the graph, is square bracket 2 to infinity. The range of f that we see from the graph, the y values used by points, is square bracket 0 to infinity. This range corresponds to that restricted domain. And we don't need it, but the range of the inverse should look like 2 to infinity on the y-axis. And sure enough, on the vertical axis, we're using points from 2 up for that graph. Okay, so you don't need the range, but we need the restricted domain, because the graph of the inverse, this is 2 units up on that y-axis. So F inverse is just half of a parabola. And if you don't restrict the domain, you're not saying that. So a little bit subtle answer there. A couple more exercises, that, and they'll be a little bit more, I think, down to earth than these have been with restricted domain. Next exercise is very important.